Okay, so this is my second video for you. Gonna review Nexus Spine's interbodies. But before I do that, and I know I had sent you this in the past, a link to their patent, but I thought the abstract on their patent was pretty cool when you talk about the design rationale of their products. Basically says orthopedic implants, particularly interbody spacers, have a combination of correct pore size and stiffness/flexibility. When the implants have the proper pore size and stiffness, osteocytes are able to properly bridge the pores of the implant and then experience a proper compressive load to stimulate the bone cells to form bone within the pores. It says an implant includes a body formed of an osteoconductive material, i.e. titanium, and having a stiffness between 400 and 1200 megapascals. Additionally, the body includes a plurality of pores having an average size between 150 and 600 microns. Those pores permit the growth of bone therein. The body is formed of packs of coils, which may be formed using an additive manufacturing process and using traditional orthopedic implant materials such as titanium. So that's really the key verbiage in there without reading the whole patent. Their design essentially uses a bunch of small packs of coils that are basically intertwined in a pattern in order to produce really a pore size and a stiffness that is equal to that of trabecular bone. Now, most people out there making 3D printed implants are either really machining a block of titanium and then trying to roughen up the surface, which can add basically cytotoxins, or else they're printing essentially a rigid frame and then trying to use an algorithm and some type of software to build a lattice structure in there, which there's really not a lot of rhyme or reason behind the pore size that they generate in their lattice and everything else. And so you'll see a lot of implants out there that really have either the pore size is too big, they can get some surface growth, but this implant here, they're truly getting results. They're getting bone ingrowth through the implant, and they're doing it basically without the use of grafts. So I mean, that really is pretty cool stuff. Like we talked about the last time I was with you, I don't know how they essentially developed their 3D printing pattern to pull this off, but basically you have here a material that's designed to match spinal trabecular bone as close as it possibly can. So way less stiff than PEEK, way less stiff than regular titanium, osteoconductive, and they're getting great results. So here we have basically what they sent to me. You have the Tranquil C, which is their cervical option. Really, as far as I know, I have, I think I had left you the surgical technique for the T-lift cage, but I mean, basically as far as disc preparation, trialing, all that, it's pretty much standard like you would with any of the products you're using. It just really is the implant that I believe is far superior, but they do have nice tools here. Basically the inserter here essentially has a little end that when you flip this lever up, the prongs are expanded to really provisionally hold the implant. So you snap it on with the lever back, push the lever forward. There's an insert, like a tapered insert, that expands the prongs. And I mean, I'm trying to pull this thing off here, and I can't. It's on there. So this is their cervical interbody right here. And I'd really like to get this stuff to you to actually, touch and feel and play with yourself. T-lift, I mean, simple inserter, a few prongs that orient the implant, a threaded hole, line it up, rotate the knob, squeeze to tighten, and it is threaded on, locked securely. And I know the surgical technique for this, you have the hard copy. Please check it out. And then finally, from the other video, really their ALIF, obviously more robust implant there, large graft window if you'd like to use a graft. But I know, like David has said, he's like, you know, if you can scuff up the end plates and get good vascular blood flow, they're getting great results. So why bother spending money on graft material when you could essentially get just as good or better fusion without it for less money? So that's their take on that. And now I think I'm going to move on to press on next here, so I'm going to shut this off and get ready for that. Thanks.